So, we were discussing counters, use of flip flops in counter design, count of up count or down count or counting from an arbitrary count to another arbitrary count, or down from an arbitrary count to another arbitrary count. In all these cases, we use what is known as a ripple configuration. That is, the output of a flip flop drove the input of the next, was used as a clock of the next flip flop. So, in that we saw that the delay of the flip flops play a role in how fast you can count. That is not a very desirable thing, because as the number of flip flops increases, or as the count, the total count that you want to count increases, the propagation delay of the ripple counter increases linearly with the number of flip flops. So, there comes a point where the total delay of the time it takes for a count to stabilize to the next count is longer than the period between two clock, the clock period. When that is the case, then you can never have a stable count. So, we thought of wondering, we sort of wondered whether it is possible to have a counter which will be independent of the number of stages we need to count. That can happen only if the clock pulse is applied to all the flip flops uniformly at the same time, because any change in the output based on the input of the flip flop can be triggered only after the clock goes high. So, when the clock has to be active in order for the flip flops to settle down with the output, you need to supply the clock, and if you do not want the number of stages of the flip flop to decide the counting period, the delay, you need to apply the clock pulse to all the flip flops at the same time. That means, instead of feeding the clock to the first flip flop, we have to feed the system clock, the clock input clock, to all the flip flops at the same time. Then how do you control the count? Because once you put a j equal to 1 and k is equal to 1 and give a clock, all flip flops toggle. That means, if all the flip flops are zeros to start with, they will become ones after the next clock pulse. So, the flip flops will go changing from 0 0 0 0 to 1 1 1 1 and so forth. We do not want that, we want a count in a binary sequence. So, what we have to do is to look at the circuit of a counter. We call these counters synchronous counters. The synchronous counter is a counter in which the clock is applied to all the flip flops. So, let us take a 3-bit to start with, easy to handle in a classroom. I can have same negative edge triggered or master slave configuration as we heard earlier. I will call this ABC, this will be A, this will be B. Q bar, so this will be A. I want to apply the clock input to all the flip flops. So, we put a 1 1 here, and let me write the counts. So, let us say to start with, the counters were 0 0 0 initial, during the first clock period, let us say. After the first clock pulse, because this is 1 1, we want a 1 here, it will change. Now, okay, let me put it the other way. Let me not write what happens here. Let me write the sequence I want. I want this sequence. This is my desired sequence, natural binary sequence. Look at this C, the flip flop C, this one 0 1 0 1 0 1 0 1. So, it needs to toggle at every clock pulse. So, there is no problem with this JK flip flop, because once you put J is equal to 1 and K is equal to 1 and give the clock pulse, it is going to toggle, correct. So, I will not have any problem with this J 1 K is equal to 1, and I will get the desired count, desired sequence at the flip flop C output. Here, of course, if I put 1 1 JK 1 1 for the second flip flop B, if I put 1 1 here, this will also change 0 1 0 1 0 1, because I am giving the clock to all the flip flops, and I put a 1 1. So, whenever I put a 1 1, this is a toggle mode. In a toggle mode, when you give a clock, the output changes, complements itself. So, it becomes, so from 0 0 it will become 1 1, then 0 0 1 1, which I do not want. I want 0 0 0 1 1 0 1 1. So, instead of doing this, what I will do is I can use this information into, when this becomes 1, when C is 1, at the next clock pulse B has to become 1. So, instead of tying this C, J and K unconditionally to 1 1, we will connect it like this. Suppose I feed the output of C into the input of JB, the second flip flop input. This was 0, first it was 0, even though the clock was there, when this changed state, this would not change state, because the output of C was C 0, that 0 was given here, and a 0 and 0, we will also put this connected to J, both J and K, both J and K will give 1 1 0 0. So, during the second pulse, when this became 1 from 0, this does not become 1 from 0, because J and K are both 0 0. 0 0 of the clock pulse applied, it remains same in a JK flip flop. Now, next pulse appears after 0 0 1, next pulse appears. By now, C and JB and KB has been kept 1, JB and KB has, they changed to 1 in the meanwhile after this pulse. So, when the next clock arrives, at that time there will be a toggle mode here, there will be a toggling operation in this flip flop. This will toggle anyways, because I have connected to JK 1 1, so it toggles with every clock pulse. This will toggle after this, because J and K are 1. In the next clock pulse it will not toggle, because this is 0. So, every other clock pulse only the J and K of the second flip flop become 1, every other pulse, every second pulse, every alternate pulse, J and K of the second flip flop become 1 1. So, the second flip flop will toggle only once in 2 clock cycles. Is that clear? I can repeat this argument now. Third flip flop I want to toggle only once in 4 clock cycles. I want this to be connected to 1 and remain 1 for every 4 clock periods. For 4 clock periods, J and K of the third flip flop will remain 0. At that time, there will be no change in the output, no change in the output for K output of the third flip flop, A flip flop. For 4 clock pulses to remain 0, and another 4 clock pulses will become 1. Now, when do you want the transition to happen? On the clock pulse after the count 1 1 was reached here. After the 1 1 was reached here, I want this to change once, but that has to remain again 4 times for 4 clock periods. So, what I am going to do is to take these two into an AND gate, and then instead of so in both B and C are Z 1 1 at the 4th clock pulse, immediately thereafter J A and K A become 1, but the clock pulse has gone, it can only do it next time, right. So, after that it will now become 1 1, when it is 1 1 at the next clock pulse, this will toggle. I can keep this going. So, if there is a 4th position for 4-bit counter, so 4-bit counter, this is a 3 bits counter, it is a 3-bit counter, only 3 bits, 3 positions. Here these 3 becoming 1 1 1 will make the 4th flip flop toggle and remain same, because after that not all of them can become 1 at the same time. Again all of them will become 1 at the same time here, when it will become 0, which is the same as this. So, I will repeat. So, when all the previous flip flops have changed into 1, you want the toggling of the next flip flop, and that has remained for several clock cycles before the next change can happen. This is the concept of a synchronous counter, wherein the clock is given to all the flip flops, and the control, the change in the Q is controlled by the outputs of the flip flops. Earlier we tied J and K of all the flip flops to 1. So, every flip flop toggled, but then clock was delayed. The first flip flop received the system, the input clock and the system clock as I call it. The second flip flop had a clock pulse which is half the frequency of the second. Second flip flop received the clock which is half the frequency of the first. Third received a clock which is 1/4 the frequency of the first, and so forth. So, we divided the clock, used the lower and lower frequency clocks, we were able to get the toggling action slower and slower. Idea is to, first flip flop has to toggle very very fast, second flip flop has to toggle at a relatively slower rate, this slower compared to this, and so forth. Toggling is required, but need to be controlled. Earlier we controlled it by means of a clock, now we are controlling by means of the outputs of the flip flops. What is the advantage of this over the other ones, synchronous and ripple counter? Ripple counter, by the way, is also called a non-synchronous counter, asynchronous. Something which is not synchronous is asynchronous, right. So, asynchronous flip flops are ripple flip flops, ripple counters. Asynchronous counters or ripple counters are the ones we use the clock as the of any given stage from the previous output. In a synchronous flip flop, synchronous counter, synchronous counter, clocks are supplied to all of the flip flops at the same time. Control of the toggling action is done by the outputs of the previous flip flops. The advantage is only going to take after the clock pulses arrive, because this would have settled down. as soon as the previous clock pulse has occurred, take for example the transition from this to this. As soon as this clock has arrived, this would have settled down. For the entire duration of the clock, this is going to be remain 1 1. So, my j and k would have been fixed as 1 1 long before my clock is due for this flip flop. J and k will become 1 1 long before the clock comes. When the clock comes, all it needs is to take the clock period delay. So, the delay of the flip flop. So, any flip flop will change the output after 1 propagation delay. Any flip flop. Earlier, the second flip flop will change the output after 2 propagation delays. Third flip flop changes the output after 3 propagation delays. Fourth flip flop changes the output after 4 propagation delays, and so forth. That is why we found that it is not possible to carry on with a long chain, because the number of propagation delays should be the total propagation delay should be less than the clock period. That condition is not there anymore. We have to make sure that the clock pulse, the delay of each individual flip flop is less than the clock period, which is adequate, which can be amply supported, taken care of. There should not be a problem on that. And all systems which use flip flops and counting mode, most of them use this synchronous mode of counting, synchronous counting. The only disadvantage is you need extra hardware, AND gates. No? Actually, you do not need to have 3 input AND gate. Why? I have the output of this. I have to take the output of this and put it to this. So, every time I put 2 input AND gate, take the output from the previous AND gate as 1, and then. So, this will be, if you want to continue this, like this it will be. Isn't that? I do not have to go for a 3 input AND gate or 4 input AND gates. 2 input AND gates will do for each stage. So, we saw about the flip flops, the synchronous counters, non-synchronous counters, asynchronous counters, ripple counters. Basically, flip flops are used for counting, starting at any count and terminating another count, all within that 2 power n minus 1 range. With 4 flip flops, you cannot have more. With n flip flops, you cannot have more than 2 power n minus 1, 2 power n states. So, if you want to start from 0, it has to be 2 power n minus 1. Within that, you can start at any count and end at any count, or either up or down. And they can be synchronous or asynchronous, all that we have now seen. So, what is the major use of flip flops other than counting? Counting is one thing, of course. What is the original intention of starting sequential circuits here? I said we need some storage element to store a bit of information. The latch was the storage element. So, now the main use of the flip flops is in the memory. You design memories. Even though we talk about 1 bit flip flop, a flip flop which can store 1 bit, in practice you never have words of 1 bit. Usually a word is 4 bits, 8 bits, 16 bits, 32 bits, like that. For example, if you take a code, ASCII code, I said, translate our alphabets and numerals into binary code, such a code is called ASCII code. I said you get 7 bits for that, and you may have an extra bit for parity, so 8 bit code. So, I want to store that code corresponding to a particular alphabet. I need 8 bits, 8 flip flops. So, instead of building memories using single flip flops, like that, you can also have circuits or devices sold in the market which can take several flip flops at the same time, several inputs, several bits at the same time and store it. So, such a combination of flip flops is called a register. You must have used this, you must have seen this word very frequently used in digital books. Register is nothing but a bunch of flip flops, group of flip flops. A 4 bit register, for example, will have 4 flip flops . let us say they are D flip flops, because I said mostly it is used for data storage, and data storage I said D flip flop is good enough. So, you have put a D, D, D and D. Does it look like our great card? D, 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 D. Okay, D flip flops with Q's as the output. Normally, these flip flops can be controlled by a single clock. Internally, that is by connector, of course. As I said, externally, when you are looking at a device with 4 bits, as a user, you have only one clock to connect, one power supply to connect. So, all these flip flops need VCC and ground, or VDD and ground, or whatever is the nomenclature for the supply voltage. All those things we are not showing. Similarly, when we say one clock pulse, can be edge triggered, positive or negative, whatever, does not mean that these flip flops do not require clock. It is all internally connected. The clock is connected like this. Suppose I get a thing, I only see one clock, is it not? So, like that internally they will be connected. So, likewise here also I will show the clock here, but do not think that only the first flip flop gets a clock, connected to all flip flops. So, I can put any data here, or you want to put it the A, B, C, we have been using A as the most significant bit and D as the least significant bit. So, when you put this data, it should be the A should be the most significant bit, and that is okay, we can just use this way. Now, I can put this information and clock it, it will remain constant, it will remain inside and also be available here. When I want it, I can read it off. Say memory. In order to get the input into the flip flops or the register, you need to put the data that has to be stored on the inputs. When you clock it, these inputs get stored and they are available. But the problem with this would be what? The problem with this would be, I need to keep the data constantly here, because the clock keeps coming. So, you cannot design a clock for every little piece of hardware in your system you are designing, a subsystem you are designing. The clock is a common entity. Suppose I have a big digital system or digital subsystem or a huge digital circuit. There are several functional units and many of them require clock pulses for operation. So, the clock is generated and distributed commonly to all these units. Now, so this clock may be at a frequency which is much faster than the rate at which I want to put the data and remove it. Suppose I want to put the data and then keep it for a while, even when the clock keeps coming and going, I do not want to disturb the data. Only when I want to use it, I will use it, and then I will put another data. That means I want another control independent of the clock. If I do not have that second control, independent control, when I clock it, the data gets in, and if the data does not remain here, the data may be available for a short period. When it is available, I have to store it. If it is going to be available forever, then there is no need for storing it. Why should I store something which is always available, like water in this campus, right? You never have water, so you have to store it in buckets. The water has to come and you open the tap, you do not have to store it. So, you need this data only when it comes, you can store it, but I do not want the storage to be removed by the next clock pulse, because the data has been removed. Data has been removed means what? You would have taken other values which are related arbitrary values. They can all be zeros, they can all be 1, or there can be any zeros and 1 random combination, and next clock pulse will overwrite my data. Next clock pulse will put this random junk thing into my flip flops. So, my data, stored data gets corrupted, as I call it, cleared, corrupted, erased, whatever the term you want to use. So, I need another control in which the data, when it is available at that time, I want to store it, and other than that period the data will not be disturbed. So, I need a control called load control. A load. Now, I am going to make it such that the internal circuit is such that the clock will be applied only when the load is, that is, the data will be stored into the flip flops only when the load is active, not immediately when the load is active. When the load is active and the next clock pulse arrives, that can do that way, or I can say simply load will put the data in, load will put the data in. So, I can have two modes of operation. One is called asynchronous, again synchronous, asynchronous. Synchronous load means synchronous loading. Synchronous loading means the load has to be high and the clock should be activated for the data to store in. Asynchronous as soon as the load pulse arrives, the data will be stored, whatever the data found here, irrespective of the clock pulse. That is similar to the preset, reset, preset clear conditions we talked about. You can have a choice of synchronous load or asynchronous load. But the advantage is when the load is removed, the stored data is here inside. Even when the clock comes at a very fast rate, much faster than the rate at which I want to read from this memory. Give an example, I have a clock of let us say 1 megahertz, that is every 1 microsecond the clock period is 1 microsecond. So, every 1 microsecond we have an edge of the clock, every microsecond we have an edge of the clock, whereas I want to put the data here and keep it for 100 microseconds. If load was not there, after the first microsecond the data will be there, after the second microsecond it will be removed by and rewritten by whatever is here at that time, which may not be the original data. I might have removed the data was available a short period which has disappeared, and ABCD have taken random values, and after 1 microsecond my storage would be junk. So, when I look at the data after 100 microsecond, when I really need it, I will find junk inside, not what I put. Now, if the load I have this control, I can put this load at the time when this data was available and remove this load pulse, and then the clock may come and go, but then this data cannot enter in, the new junk value cannot enter in. Even though you do not have the original values, they have been removed, arbitrary random values that ABCD assume, they do not get into the flip flops until another load pulse comes. So, I can now make it after reading the data after 100 microsecond, I can put one more load pulse and capture one more set of data. Likewise, I want to clear a flip flop, that also is possible. So, I can have one more control called clear. Also, clear also can be synchronous or asynchronous, same concept. Clear removes the data, clear makes the data 0, 0, 0, 0, 0, right. So, I have this independent control. Every time, anytime I want to remove the data or make it as zeros, I can use a clear input automatically, irrespective of what is there on ABCD, all the flip flops will assume zeros. Again, that can be done with the clock pulse or independent of the clock pulse. When it is done independent of the clock pulse, it is called asynchronous. When it is done along with the clock pulse, only when the clear will work, only with the clock edge, without that it will not work. That is called synchronous clearing. When as soon as the clear pulse is given, if the flip flops change to 0 0 0 0 independent of the clock pulse with a 0 or a 1 or an edge, then we call it asynchronous clear. So, in short, I have these registers which are bunches or groups of flip flops, bunches or groups of flip flops, which are several things. I can put the data in and keep it as long as I want and take it off, read it off and use it. I want to use it again the same data. I can have a data which is stored and read it off again and again. That is also possible, because as long as I do not load new data in, the data going to remain. It is not going to, once you read off, reading off is nothing but using these values, that is all. When you read off a value, does not mean that the data is destroyed, it is non destructive. Or I want to change the value, I put a new set of value, load it, and I want the data to be zeros, I clear it. These are all very convenient control inputs, which will be used in a circuit when you design a larger systems. We will see how to use some of these things in our subsequent lectures, where we will use some of those designs using these counters. So, data storage is a major application of flip flops. Counting is one of the applications. Data storage is a major application. Division by factor of 2 is another application. But data storage is a major application, and usually D flip flops are used for that, because we need only one input for data, and the data can be manipulated by use of clear, and the time at which data is put and cleared is controlled by two inputs called data and clear, in addition to the clock, which is universal for the whole system, and that clock may not be the rate at which we want to put in the data or remove the data, clear the data. If it is the same, of course, you do not need all this, but it is not generally not true, because I may have different registers in different places in my system. Not all registers get stored and cleared at the same time as frequently as the clock arrives. Some of them may have to store data for a longer time, some of them may have to store data for a shorter time, and none of them may be able to store the data or clear the data at the rate at which the clock arrives. The clock frequency is decided by so many other factors. So, we do not want to get into it, because speed of the system, etc., will decide the clock period, clock frequency. I do not want that to affect my, there is only for a short duration of a nanosecond or a microsecond and my data will be available, useful. It is no use, as good as not being stored. If you have a data and it is going to be cleared immediately, what is the point in even storing it? A variation of this register is called a shift register. These are inputs which are applied to all the flip flops at the same time. Clock is applied to all the flip flops at the same time. Load is applied to all the flip flops at the same time. Clear is applied to all the flip flops at the same time. Outputs are available parallelly. These are, on the other hand, if I have a operation where I have a first D flip flop, the output D, output Q is fed into the second flip flop, and the output Q is fed to the third flip flop, and output Q is applied to fourth flip flop. Of course, any number of flip flops. I am just giving you 4 as an example. Of course, I clock them synchronous. Here afterwards, unless I specifically say it is asynchronous or ripple counter, we will use synchronous counters, where clock is applied to all the flip flops at the same time. when we need to use a ripple counter, specifically I will tell you it is a asynchronous counter or a ripple counter. So, this is my clock. Instead of putting the data simultaneously in all these flip flops, and now I am connecting the output of the first flip flop to the input of the second flip flop, output of the second flip flop, the input of the third, and so forth. Now, whatever data I put, after every clock pulse, that data will shift to the next flip flop, right. Suppose initially I put a data, so I call this ABCD. Initially, and then after first clock pulse, because this is connected here, this connected here, this connected here, this one will go here. Whatever I give is the value, I will call this input value, IN, that IN will come here. Is it not? The new value. And this 0 will be bumped off, gone. After the second clock pulse, this would have moved here, this will become 1, this will become 0. And what we will have here will be in 2, second input, whatever it was. After third, in 3, in 2, in 1, 1, and so forth. I keep shifting the data from one flip flop to the next flip flop, to the next flip flop, to the next flip flop, to the next flip flop. Such a arrangement of flip flops is called a shift register, because it shifts. It is a register in the sense it stores data, but it keeps shifting the data from flip flop to the flip flop to flip flop to flip flop. So, shift register. So, again I can draw this as a one block, even though we do not have to show all this inside. So, 4-bit shift register. SR stands for shift register in this case. So, I will not show individual connections and output of this. I put the data here, this input is called a serial in. The 4 flip flops of output QA, QB, QC, QD. And 4 inputs called DA, DB, DC, DD. Now, DD can also be, QD is also the serial output. Suppose I have now various combinations. I can load a value of DA, DB, DC, DD, all of them at the same time, and then start shifting. Shifting is always from one flip flop to the next flip flop, but the way in which I load the flip flops can be one at a time. Serially I can put one at a time. Initially I can clear all the flip flops. I don't even have to clear the flip flops. I don't even have to clear the flip flops. I start pushing in data one after the other, it will go and get loaded, whatever way it is. Or at the same time I want to put all the flip flops at the same time, different values. So, I can have the option of serial load, parallel load, or serial input, parallel input. Likewise, I can read off the flip flops QA, QB, QC, QD all at the same time, or I can look for the output at serial output, last output, right. So, I can have a serial out and the parallel out. So, they need a clock which is common to all of the flip flops. Clock is common to all the flip flops, as I said in the case of registers. So, when I put parallel data in, how do I get them into the flip flops? By loading. So, I need a load which is common to all the flip flops. I can have a clear also which is common to all the flip flops. So, I may have all these features in our shift register. I can clear all the flip flops and make them 0 to start with. I can load a new set of values by putting A, B, C, D different values and loading it on by using load. After clearing or loading, if I start the clock will shift during the every clock pulse, the clock will shift the output from one position to the next. That is the main operation to do, and at any point in time you can freeze what you have and read off the values parallelly, or you want to read serially, you have to keep applying clock till you get all the bits out. So, that means I can have 4 different combinations of operation. I can have serial in, serial out flip flops, serial in, serial out, serial in, parallel out, parallel in, serial out, parallel in, parallel out. These are 4 combinations possible. I can give the input serially, take output serially, 1 bit at a time. I will keep loading. This operation is a minor operation, in the sense I keep loading and gets the output. Whatever I put here comes out here after the delay of the number of clock pulses equal to the number of flip flops, in this case 4 clock pulses. Whatever data I keep giving here, that keeps coming out here after a delay of 4 clock pulses. So, 4 is only an arbitrary number. I do not have to have only 4 bit shift register, I can have an 8 bit shift register, I can have any number. Usually 4 and 8 are available as a product, as an IC in the market. So, either use a 4 bit shift register or 8 bit shift register. So, after 4 clock pulses or 8 clock pulses, as the case may be, whatever you put comes out. So, this can be used as a delay element, that is all. Suppose you want the data to come, but then the same data has to go out after a particular delay. I can use this serial in, serial out mode. Number of the delay is equal to the number of clock pulses times the number of flip flops times the clock period. There are 4 flip flops, it is 4 clock pulses delay, 4 clock periods. 8 flip flops, 8 clock periods delay. Serial in, parallel out is when you have the serial input data and I want to take it parallelly, this is called serial to parallel conversion. What happens is, some applications I have a serial input data coming in, but I have to wait for the whole bit. For example, let us assume a ASCII code 8 bits. I have an 8 bit shift register. I get an ASCII code from some other device. Unfortunately, that device can only transmit 1 bit at a time. Unfortunately, that device which is supplying the ASCII, that keyboard, has only a serial connection. So, the 8 bits of the ASCII, including the parity bit, 8 bits of the ASCII keep coming 1 bit at a time, 1 bit for every clock period, but I cannot process this until I know what ASCII code it is. I cannot process until the ASCII code is completely built, then I can store it or do whatever with it. This is an application where serial input, parallel output Parallel output is required for processing, serial input is the limitation of the device, like a telephone modem. You know that in a telephone modem, what is called dial up modem, the data comes serially because you have a pair of lines. No, telephone line is a pair of lines. You use it in your computer. Do you do it at home? No? Everybody does it now. Today grandmothers do it. I think you should be able to do it, right? Take this. They know more computers than we do now. You put this thing into the computer. Because the telephone line can only, the limitation is the telephone line, not the generation of data. I want to send a mail to you, my computer also can give you parallel output, your computer can also process parallel, but in between the medium is serial telephone line. So, I have to convert my parallel data into serial mode data and send it to you, that is what my modem does, and your modem gets it back into parallel, is that right? So, these two things are covered, serial input parallel output, parallel input serial output. Examples are modems. Finally, this parallel in parallel out, parallel in and parallel out is similar to the register, where I want to put in the data and take it out, that is all. I load it, I take it. Disable the load, it will remain as long as required. So, this is same as a register operation. Shift has no meaning in this. If you want to put the data and take it out as it is, where is the question of shifting it? There is no need for shifting. A shift register becomes a normal register operation in this mode. It is a very powerful device, as I said, it can be used for many things, for storing, for delaying, for converting parallel data into serial, converting serial data into parallel. And I only talked about shifting to the right. By a proper connection, the output of this flip flop can be connected to the input of this flip flop, output of this can be connected to the input of this, output of this can be connected. Is it not possible? Output of this I connect to this, output of this connected to this, output of this connected. Supposing I take the output of this and connect it to this, output of this and connect it to this, output of this and connect it to this becomes a left shift register. So, I can have a shift left shift register, shift right shift register. So, a shift register can have a serial input as a data input, parallel data input, serial data output, parallel data output, it can shift left, it can shift right, and if all of them are given in one, you can buy a appropriate shift register. I can buy a shift left 4-bit shift register with serial input and serial output, or you can have a register which you do not need a shifting, that is a register. So, if you want all of these features, you do not know which one you will use. I want shift left feature, shift right feature, clearing feature, loading feature, serial in feature, serial out feature, parallel in feature, parallel out feature, all of them I want, but I do not know what I will use when. Such shift registers are available, either 8-bit shift registers or 4-bit shift registers. Such shift registers are called universal shift registers. Because they can do all the things that you want to, but of course not all of them at the same time. You have to configure it for one particular operation. You configure a shift register for a shift left operation or a shift right operation, or parallel load and serial out, serial in, parallel out, and whatever. These are available in market commercially, but you should know what is inside. Inside, after all, nothing. So, I have reduced the myth of all these registers, counters, this, that. You have 2 chapters in your book on flip flops, registers, counters, right. So, basic storage element of a latch connected to the clock is a flip flop, and we can use flip flop in so many different ways to get all those different things. Similar to what we did in the case of gates. Only gates and gates we had so many other applications. We call them adders, we call them parity generators, we call them parity checkers and all that. Okay.